this meeting?
Yes, it is in progress.
Yeah, thank you. Okay, now Seto-san, what PC is?
Yeah, now we share the voice in this room, so we can please go ahead.
Okay. So, Seto-san, could you share the agenda of the meeting?
Richard, kannst du mich hören?
Roman, ich kann dich hören.
Okay.
Maybe now we see the agenda, right?
Yes, okay. So, okay, everyone is okay for the meeting. So, shall we start the meeting? Good afternoon and good morning. No camera. Please wait.
So,
Okay. Thank you. Okay, I'm Naoki Miyato from QST Rokkasho. I'm acting as a technical coordinator of the JA side for the IFERC-CSC and responsible for operation of JFRS-1 supercomputer system. And so JFRS-1 is at the Rokkasho and is in the same room Helios was operated. And yes, the purpose of this workshop is to share the main result.
Vieni, dai, vieni che sto facendo la riunione. Vieni, dai, ma. Allora, guarda quanti piedi sono, da una parte all'altra. No, che stai facendo? La lunghezza.
Somebody is speaking.
Inizia dal capo, via.
So please mute yourself if you are not the speaker.
Richard, you are host. Could you mute them?
I can't. I'm trying to find out who is speaking. I don't want to mute the speaker as well. So I can do that indeed.
Okay, thank you. Thank you for cooperation. Yes, the purpose of this workshop is to share the main results from the simulation projects using JFRS-1. And so, as you know, BA phase 2 has started in April 2020. The objective of the IFERC-CSC is to provide the computer resources to advance high priority simulation studies for ITER, JT60SA, and fusion reactor in general. For the last cycle from April 2020 to March 2021, JFRS-1 computer resources were allocated to 27 projects, JA and EU projects selected by the EU-JA Joint Allocation Committee. So this time, there are 5 talks from the JFRS-1 project as found in the agenda. So you can see now the agenda on the screen. 4 talks are related to the edge physics area. It's one of the important topics for fusion. And the one talk is related to the gyrokinetic simulation. Yeah, it's of course a big user of the supercomputer. So, yes, okay. So now you can see the agenda of the workshop. The first speaker is Dr. Seto from QST. The title of the talk is Interim Report of Talk Edge about first-class extension for interplay between flow, low and MHD, and turbulence. And the time for one talk is 30 minutes. It includes the Q&A time. Okay, Seto-san, please start your talk.
Thank you, Chairman. Please wait to change the presentation. So maybe now we can share my presentation. So thank you, Chairman. I'm Haruki Seto from QST and the principal investigator of Project Top Edge. Today, I will propose please wait. Maybe now we can see my mouse pointer. So I will report an extension of nonlinear MHD code about for simulating interplay between flow and low MHD mode and turbulence. This is the outline of my talk. First, as an introduction, I will briefly explain about code and objective of Top-Edge project. And second, I will explain the numerical issues of Poisson solver in code and new Poisson solver developed for low MHD modes developed in this project. And then I will share with you some numerical results of linear and nonlinear tests using the new Poisson solver and summarize my talk. So the about code is a plasma fluid simulation framework in curvilinear geometry using finite differencing schemes. Also for Tokamak simulations, about calculates low-end and high-end resonant plasma structure with high accuracy in complex boundary geometry in Tokamak plasmas, including X-points domains, by using the special coordinate systems. But as a side effect of usage of such special coordinate systems, for the Node++ employs a float ordering assumption in Poisson solver for the resonant mode. Resonant mode means N not equal 0 modes. Then Poisson solver is required to calculate the flow potential from vorticity in reduced MHD model. However, the float ordering assumption may not be accurate for low N modes, especially in diverted geometries. Top-Edge project is a 2-year project to extend BAT++ framework for Tokamak edge simulation, solving interplay between the N equals 0 flow and low N MHD and middle M and high N ballooning modes in diverted geometries. This extension is important to improve the handling of current-driven errors, resonant perturbations, and full annual torus edge turbulence simulation, etc. And in the last cycle, float ordering free Poisson solver designed for ON mode was developed in this project, and which is the main topic of this talk. So BAT++ describes differential operators with radial derivative in flux defined in the flux surface coordinates and the parallel derivatives defined in the field aligned coordinates. This special coordinate system is known as a shifted metric and radial derivative method, which is reported in Tatson's 2009 paper, CTC paper. But for Poisson solver cannot define as a boundary problems straightforwardly by using this special methods because due to the coexistence of radial derivatives to be defined in flux surface coordinates and the parallel derivatives to be defined in field aligned coordinate systems. And in this talk, the Poisson solver is designed for the vorticity using Bushnell approximation, which means density perturbation is much smaller than equilibrium values to linearize the Poisson solver. So to define the Poisson solver in one coordinate systems, so there are two ways to define the Poisson solver in present BAT++. For the resonant modes, so to to define the Poisson solver as a boundary problem flux surface coordinate for resonant modes. So fluid ordering assumption, which means neglects the y derivatives in the defined in the field aligned coordinate systems. By using this approximation, so the perpendicular Laplacian operator can be defined in the flux surface coordinates. And for n equals 0 modes, on the other hand, a Poisson solver for n equals 0 mode is defined as a boundary problem in field aligned coordinate system using the toroidal symmetry property of the n equals 0 modes. So now perpendicular Laplacian operator is defined by the differential defined by field aligned coordinate system. However, the usage of fluid ordering assumption in resonant mode is not valid, maybe not valid for the low n mode, especially in diverted geometries. So in this project, so new 3D Poisson solver defined in the flux surface coordinate is designed for low n modes with flux surface coordinate matrix as shown in here. So the perpendicular Laplacian is defined by the only consists of the differential defined in the flux surface coordinate systems. So this Poisson solver can give the self-consistent flow potential without fluid ordering assumption for low n modes. But as a side effect by the usage of standard flux coordinate systems, toroidal grid resolution must be fine enough to resolve the toroidal structure for low n modes. And this solver employs a petty iterative solver with hyperplane conditioning. And this solver is applicable for non-diverted geometry, so circular geometry and single null and double null diverter geometries. And now bottom panel shows workflow developed in this project. So from the left, so sorry, vorticity at these time steps and the flow potential at the previous time steps is inputted as the left-hand side value for Poisson solver and initial guess for petty iterative solver. And these values are converted to the flux surface coordinate in Fourier space. And the flow potential at this time is calculated by 2D Poisson solver for the toroidal mode less than or equal to NFCS. This is a free parameter we choose. And for the flow potential, as NFCS is calculated by the 2D Poisson solver with fluid ordering assumptions. And these results are merged and converted to the transforms to the field aligned coordinate system like that. And from this slide, I will share with you the verification test by ideal ballooning mode instability in shifted circular geometry here, and then the verification test by the resistive ballooning mode instability in single null diverted geometry. So 2D Poisson solver test is tested by comparing the linear ideal ballooning growth rate in circular geometry by using 2D Poisson solver and 1D fluid ordered Poisson solver respectively. In this test, the following three-field linearized reduced MHD model is employed for the governing equation of ideal ballooning modes. And in this test, the well-tested strongly ideal ballooning unstable circular geometry is employed. And the ideal ballooning mode appears around the Q equal to the flux surface, where the pressure gradient takes a maximum. And for the test with 1D Poisson solver, I use 64 toroidal grids, and for the test with 2D Poisson solver, so we use 512 grid points in toroidal direction. And the linear growth rate is evaluated as a fundamental mode of 1nth annular weight torus domain, and the toroidal derivatives are evaluated with the first Fourier transform. Now the left panel shows the benchmark results. So the growth rate obtained by 1D Poisson solver is colored by red, and the growth rate obtained by 3D Poisson solver is colored by blue. So these values are very similar. So maybe we can only see the only blue circles. And now I also show the eigenfunction of part of the pressure of n equal 5 moles obtained by 2D Poisson solver and 1D Poisson solver. So this test shows 2D Poisson solver works well for the ideal ballooning mode test in the shifted circular geometry. But this is just a test with pressure gradient modes. And now 2D Poisson solver test with current-driven linear instabilities in preparation. Next, 2D Poisson solver is tested in the single divergent geometry, comparing the linear resistive ballooning mode growth rates by 2D Poisson solver and 1D Poisson solver. Now, the ballooning equation is the linear resistive ballooning model, three-phase resistive ballooning model with numerical dissipation in vorticity equation. It should be noticed that numerical dissipation are required for the numerical stability for both 1D Poisson solver and 2D Poisson solver tests. And now this panel shows grid geometry used in this test. And this geometry imitates east geometry, and in core region, so this grid has about 195 grids in radial direction and 192 grids in toroidal direction. And the right panel shows the safety factor profile and pressure profile respectively. And the resistive ballooning mode reported in the next slide appears around 9. Psi equal 0.96, so Q equal about 5 to 6. And now in this test, resistive n equals 3 and 4 resistive ballooning mode is tested in the 1nth annular wedge domain. Now this is the result. So in divergent geometry, growth rate obtained by 3D Poisson solver colored by blue is slightly different from that obtained by 1D Poisson solver colored by red. The difference is about 6 to 8%. However, in both cases, both Poisson solver, as shown in the right panels, so the resistive ballooning eigenfunction are clearly obtained in both Poisson solver tests. So further tests is required, especially for the mesh convergence test in toroidal, the 2D Poisson solver case, because now we only use 200 grid in toroidal direction. It may not be sufficient to resolve the toroidal mode number 20 or 30 in this case. And finally, I will report the preliminary result of pedestal collapse simulation in annular full torus domain in shifted circular geometry. In this preliminary pedestal collapse simulation, the four-field reduced MHD model describing the resistive ballooning mode and resistive ballooning mode and drift wave instability. So I will skip the detailed explanation, but this equation is the same as used in my paper published in 2020. And also the simulation setup, but the grid resolution is the same as this paper. And for the full torus annular wedge simulation tests, the resolution is as the following. So 112 grid in the radial direction from 0.4 to 1.2, and 128 grid in toroidal direction, and 56 grid in toroidal direction. And in this simulation, the toroidal mode from 0 to 80 modes are taken into account. And from 0 to n equals 0 to 4 modes are solved with 2D Poisson solver without float ordering assumptions. And the toroidal mode higher than 5 modes, higher than and equal to 5 modes are solved with 1D Poisson solver with float ordering assumptions. But this is just a test run for the 2D Poisson solver, and radial and toroidal resolution may not be enough for production run. And in this paper, so we need 1,500 grids to resolve the very fine parallel current filament structure appearing during the pedestal collapse. And we need 160 toroidal mode number to get the inertial region during pedestal collapse. With the setup in the previous slides, the pedestal collapse is triggered by the resistive burning mode instability, whose peak is around n equals 32. And now, right panel summarizes the temporal evolution of the energy loss in the case of full torus simulation, colored by red, and the 1/5 torus simulation reported in my previous paper, colored by blue. And for full torus simulation, it takes for this simulation, 2004 is required for 2 days. Maybe this is acceptable computational cost. And for the temporary evolution of element, the energy loss process. So in case of 1/5 torus case, energy loss grows rapidly as pedestal collapse occurs. On the other hand, for full torus case, energy loss increases gradually at the first stage and then increase rapidly. Now, these two figures summarize the time evolution of energy loss with white colored, maybe someone type keyboard. Okay, I will give my talk. So energy loss, temporary evolution, the energy loss is colored, is expressed with white solid curve and left vertical axis, and the toroidal mode spectrum of perpendicular kinetic energy normalized at every time step is shown with the color map and the right vertical axis. And now the right figure is results obtained from the 1/5 torus case, and the right panel is a result obtained by full torus case. So in both cases, initially unstable modes around n equals 30 here and here trigger the pedestal collapse. But during the pedestal collapse, and in pedestal collapse, energy cascade from n equals 30 modes to higher for toroidal modes, and inverse cascade from n equals 30 to low n mode also appears in the color map. Now, the inverse energy cascade process during pedestal collapse are zoomed up in the bottom figures, and for the 1/5 torus case, n equals 5 mode is excited before n equals 0 mode, but n equals 20 to 35 mode here are still dominant mode, and energy loss increase rapidly by turbulence transport due to these modes. On the other hand, for full torus case here, sorry, low N mode are strongly excited via inverse energy cascade process here. So as shown in data, first stage N equal 4 is dominant, and the peak shift to the low N regime, and finally N equal 0 mode is dominant in this case. And so in that stage, the low N mode is dominant. So pedestal energy loss gradually increase as shown with quite solid curve. But once high and middle N modes around N equal 2 or to 40 modes get excited, after that, energy loss is rapidly increased by turbulence transport. These figures are some temporal evolution of perpendicular kinetic energy. The left is a result obtained from the 1/5 torus case, and the right is a full torus case, respectively. So when we see the full torus case, we can find the amplitude of the most unstable modes significantly decrease at the pedestal, at the beginning of pedestal collapse. This is due to the increase of unstable toroidal modes driving pedestal collapse in simulated system. And the zonal flow intensity obtained in nonlinear states are almost same in both cases. But as shown clearly, so in case of full torus simulation, pedestal collapse has two phases. Before discussing the two pedestal collapse in the full torus case, we see the so now bottom figure shows the toroidal spectrum in linear phase and the toroidal spectrum just before the pedestal collapse for the 1/5 case and full torus case. So the resolution in toroidal spectrum is different, but they show the similar tendency. So the inverse energy cascade excites resonant low N modes like that, rather than N equals 0 mode at the beginning of pedestal collapse. And now we see the temporal evolution of toroidal spectrum in full torus case after the first collapse. So the peak position in low N mode gradually shifts to from N equal 4 to N equal 2, 1, and maybe in this case, the amplitude of N equals 0 and 1 is almost the same. And in the second collapse phase, so as shown in the previous slides, so low N mode, middle N to high N mode trigger the second collapse. After the second collapse, so N equals 0 mode, so zonal flow intensity becomes a dominant component in perpendicular kinetic energy spectrum. However, the physics mechanism behind this process has not been investigated yet, which is left for the future work. Finally, the time averaged spectrum after the pedestal collapse averaged from 500 to 1000 are summarized in the bottom figure for the 1/5 torus case and full torus case. So both spectrum have similar trends. So the two peaks at the middle N regime, N equal 25 and N equal around 40 for both cases. So taking full toroidal spectrum may be important to study the dynamics during pedestal collapse triggered by high pressure driven modes and less important for the turbulence analysis after pedestal collapse. But this is just a speculation, and further studies are required to make conclusion. So let me summarize my talk. So 2D Poisson solver for low N mode has been developed to extend about for tokamak simulation, solving interplay between N equals 0, low N, middle N, and high N modes in diverted geometry. And the verification test of 2D Poisson solver shows good results, but for diverted geometry case, there is a difference between 1D full ordered Poisson solver and 2D Poisson solver. Further test is required to qualify the impact of full ordering assumption, especially in diverted geometry. And preliminary pedestal collapse simulation in annular full torus domain in shifted circular geometry is also carried out. So pedestal collapse simulation in full annular torus domain using the 2D Poisson solver works with acceptable computational costs. So 2004 for 2 days. Introducing low N mode may change the dynamics during pedestal collapse driven by high N resistive burning instability, but may not change the turbulence property after pedestal collapse. But we need the production run with high resolution. For example, the radial grid is about 1000 and the toroidal grid is 500 to introduce the toroidal mode up to 100 or 160 for further analysis. And now this slide summarizes research plan of top page in this cycle. So for linear verification test, further ballooning type instability test with ion density profile in diverted geometry is planned. And also the 2D Poisson solver with current-driven instability. So kink mode or peeling mode is planned to check whether my extension can capture the type 1 errors. And for nonlinear simulations in diverted geometries, so pedestal collapse simulation in full annular diverted geometry, single null diverted geometry is planned. So we already get some nonlinear simulations, some nonlinear results in single null diverted geometry, but further code check are required before presentation. And for simulation of transition from type 1 to type 3L, including resistive ballooning mode turbulence in diverted geometry with full toroidal spectrum is also planned. This is the main research target in this cycle. So in this campaign, so Elm class is Elm class is numerically investigated in series of eta-like equilibria with different pedestal collisionality, and the maximum simulated toroidal mode number is also scanned to investigate the impact of resistive ballooning turbulence on energy loss during pedestal collapse in type 1 elms, type 3 elms, and their intermediate regime. I believe this is useful for understanding dynamics of elms in ramp up and ramp down phase. That's all. Thank you for your attention.
Okay. Thank you very much, Seto-san. Now the comment on the question. Hi. So someone has a question or comment. Please turn on your microphone and please speak. Bekele-san, please.
Hello. Very nice talk. I have actually 3 questions. In the beginning, when you showed X-point geometry, you did some linear tests for the moment, as I understood. But what about boundary conditions on the diverter plates? Are you going to install them? Because this is very important for elm crashes, for example. We know it from modeling, nonlinear record.
So far, no cis boundary condition is applied on diverted geometry. So just the Neumann boundary condition is applied on diverter targets. And now I implement the cis boundary condition on diverter
Okay, so
plates.
you know that after all, for the nonlinear modeling, you should do it properly. And this is one question. Then when you showed this turbulence and you did it in circular geometry, but okay, since you are using a lot of harmonics, it's a very nice result anyway. But to reproduce pedestal collapse, my question is, I don't see any signs of any stabilization of these modes because you need it to reproduce, for example, Elm cycles, or because your time is very short because of the high number of harmonics. Is understood in Bout++, you have this diamagnetic stabilization. Normally this mode should be stabilized after all, and the pedestal will grow up again. You'll have the second cycle. What are your thoughts about this? Is it possible? Are you going to try maybe with lower number of harmonics?
Maybe if I catch your question correctly. So
no, my question is it possible to do cycles? Because looking like this, see any fulfill of the pedestal again?
So now there is no mechanism to reveal the boost slap current and also the pedestal pressure. So there is no sync term or a Kruk-like operator to recover the parallel current. So this is just a simulation for one Elm crash.
Just only one line. And the third question is about parameters. With Bout++, you can use rather low resistivity, low viscosity, realistic.
In this pedestal collapse simulation, so resistivity is set to 10 to -8, but we use a relatively large hyperresistivity. So resistive skin depth is determined by hyperresistivity rather than resistivity. But I think this value is not so small, not so large. But as I read in here, so now density profile is monotonic over the simulated domain. So we have to introduce hyperbolic tangent-like density profile to do the, for example, experimental analysis using this code. I understand the importance of the introducing such a modeled profile.
And they are constant or they are temperature dependent, your resistivity?
So now only density is constant and the temperature is given by the pressure profile divided by
I mean, the resistivity. Yeah, resistivity is constant or temperature?
Yes, so the resistivity is not consistent with the pressure.
Okay, now just time is over. So if anyone have further question, please use the chat for communication. Okay. Okay. Thank you, Seto-san. So yeah, next speaker is Dr. Chagaya from IPP Czech Academy of Science. And the title of the talk is New Properties of the Collisional Sheath. So please start, Dr. Chagaya.
Thank you, dear Chairman. Good morning and good afternoon, dear colleagues. It's my pleasure to speak about simulations, about new properties of the collisional sheath. Before doing this, I want to thank organizers for inviting me and giving this possibility. So we have a number of sub-projects undergoing under IFERC-CSC, and usually we simulate a whole scrape-off layer for different machines and for different stationary and Elmy and Bloby elms too. So on the right hand side you can see elms at the jet. And arises question why we are concentrating on the plasma sheaths we even do not see in this picture, because if you consider this profile of the temperature, electron temperature, sheath is so small that you don't see. So the question is why we are interested in this. And I will speak about this in my presentation. So outline is following, so it's motivation. Then I discuss obtained results. Then I describe our codes. At the end, before coming to the end, the conclusions of these simulations. And at the end, I want to speak about our experience of running jobs under IFERC-CSC. I think is a good place to speak about this. And starting from motivation. So you can see on the left-hand side, it's a cutout from a pioneering paper by Kodura in 1982, so about 40 years ago, about magnetized sheaths. And if you go now about 10 years ago, simulations, so 30 years after this simulation, nothing, I mean, not many things have been changed. So what you can see in these simulations, of course, the capabilities of computers were absolutely different. This was done by serial code, 200 cells, and this was done about 10 years ago, probably 500,000 or maybe 300,000 cells. So it's different capabilities, but there was no big difference in physics. We can clearly say the upstream plasma, so-called collisional sheaths, when the collisions are dominating, then we have magnetic pre-sheaths, when magnetized plasma is dominating over collisions. And then we have, people call it Debye sheaths, but it's not Debye sheaths, we call it electron sheaths, which is caused by electron scraping off of the wall due to very finite gyro radius. The question is, so what can be fundamental when we have these two pictures now? And this appeared about, so before coming to this point, we have to consider how this sheath model is derived. So we have a number of scales, starting from the roughness of the surface, which usually of the order of not more than 10 microns, otherwise it's just damage or just a cracked surface. Then we have the lambda Debye, so the Debye sheath typical length, so it scales in this parameter density. Then we have ion gyro radius, and finally we have mean free paths, mainly for the Coulomb collisions. And these are conditions, and these conditions have to be satisfied to have this sheath model which I described before. And in most cases, this is satisfied, leading to main sheath outcome, sheath model outcome, which is particle flux to the wall, which is given by this expression, actually Mach number equal 1, and heat flux to the wall, which is normalized heat flux to the diverter or just any wall, with just ion saturation current times electron temperature, and this is roughly 10. And these simple expressions are based on any plasma-ball interaction model, any Langmuir proper modeling, where, just to explain that CS is, of course, its usual sound speed. The question is, what happens when this scaling is not satisfied anymore? And first of all, let's see. Yeah, I actually should be opposite, but okay, so let me come first here. And in reality, if you consider this, just take one of these parameters, the Coulomb collisionality, and just compare what can be imaginary, let's say, diffusion due to Coulomb collisions, just classical diffusion, normalized to the projection or normal to the wall, which scales like this. And let's see, according to sheath model, this should be very small. So if you now consider typical next generation machine parameters, eta and demo, we can see that in the region where we can neglect really collisionality of sheaths, this is this region, we have some part of eta, but we all have no chance for demo. And mostly eta in a stage, the parameter region, when you cannot neglect Coulomb collisionality at all. Same for demo. And this causes some differences, and as you'll see later, probably fundamental differences in the sheath model. And by the way, we came here, this is quite simple calculations, but we came here not directly to this expression. We came here due to presentation which was done a few years ago and work. when we are just simulating a large number of scrape-off layers for absolutely different collisionalities. So here you can see density of the sheath edge. And we were studying how position of the sheath edge depends on the density. And you find out that in our machines, our day machines, including jet and so on, starting from very small to large, it somehow stays about 5 to 10 gyro radius, which is within the classical model. And then for eta-like parameters, we had a jump. So in some cases, we had no Mach number 1 was never achieved, or it was achieved just in front of the wall, which was the distance was much smaller than ion gyro radius, so it was not really sheath entrance. And this was the main motivation. So what's going on here? So in order to make let's say a quantitative study and concentrate just on the sheath, we decided to consider not the whole scrape-off layer, but just sheath. And we consider different collisionalities. So starting from classical, which is actually in real machine, so it's a compass sheath autodiverter, which is very near to the classical because practically fully collisionless, and going up for different densities. These are profiles. Here we have a diverter plate, you have upstream plasma, and these are density profiles for different cases. For simplicity, we consider most of cases just ions, main ions, electrons, and neutrals. And one consider to see maybe we are missing something, consider a full model, which is given here. When we put it also quite complex recycling, so full recycling model, including molecules, excited state, dissociation, recombination, and so on. But there's no big difference, as you can see here. Just to classify the simulation, these were one-dimensional simulations, and the necessary resolution was from 10 to 5 to 10 to 6 cells. The CPU time required, so the core hours was so 100,000 to 1 million, 5 times million core hours, so which is very unusual for sheath modeling, but this is necessary, as you will see, for high densities. We used to not make some artificial effects due to numerics. We used extremely high number of particles, which was equal to real number particles. And we reach eta relevant densities here. And these are considered conditions. So the results are, I'm starting directly from results. So you can see that if we consider, let's say, our then machine parameters, we have Mach number profiles, which are satisfying our conditions. So some of them are Mach equal number is satisfied a little far from the wall. This is kind of degenerate case when you have no neutrals. So these two cases, no neutrals, and plasma starts to becoming supersonic quite far. But anyway, Mach number is equal 1 reached. And then we have a classical model with presenting the conditional presheath, and we have Mach number equal 1. This is typical jet-like case. And whenever we go to high densities, we never reach Mach number equal 1. So we confirmed what was obtained by large scrape-off layer modeling, much by higher resolution. So these two cases are, one is simplified model, only one ion type, and the another one is model with molecular ions and atoms too. So question is, this is not the whole story, because unfortunately, it's not only Mach number 1 is not satisfied, but plasma is demagnetized. So it's quite far from the sheath entrance, which we assume usually about 10 gyro radius distance from the wall. And this is the wall is here, or diverter plate is here. We see that the projection of the parallel velocity to the, or let's say no colloidal velocity to the parallel direction in one-dimensional case should be same, and its plasma is magnetized. But whenever you come to very high density sheath region, even not entering sheath, it starts to demagnetize. And in the distance where it's just usually assumed to be sheath entrance, this demagnetization is quite significant. Another important point is we can just see how now parameters deviate from the classical one. So I put Mach number. So the idea is now how to define G-edge, sorry, or jumping. And in these cases, when we do not have, we have demagnetized plasma, one has to put G-edge at the place where last point where plasma is still magnetized. I want to say that plasma parameters do not change strongly because this distance actually is not so big. But for strictness, we put now G-centrals here. If you consider now this G-central definition for a very high densities and consider now main G parameters like Mach number, normalized heat flux, normalized to classical one, which is 10, and also consider to neutral particle load to the diverter, which is in most of cases neglected, we end up with this story. So we have for the densities at the G-edge, which is just 10 to 19, typical for a few times 10 to 19, highest densities for our day machines. We still have a quite good agreement with classical models, or Mach number 1 is reached. We can see that it's quite, sorry, it should be inverted. So it should be 1 over sound speed. Sorry for this. It should be 1 over sound speed. It's 1 over Mach number. I was surprised why it's each one. And we have a heat load, also classical. And starting at some point, we have quite significant neutral load to the diverter plate. But whenever we come to ether-like conditions, Mach number is significantly lower than the it should be expected, because originally here was the classical flux to the actual one, which was inverted. So you understand that it's inverted Mach number. And we have also extremely high, extremely low heat load. Should be all these parameters inverted, sorry, these two. And we have very strong, dominant heat load due to neutrals. So these are the main simulation results showing that we have to be very careful when we go to high density plasma, because we can very strongly overestimate heat flux, particle flux, and maybe do not calculate correctly the heat flux. I will say why I do not want to consider that we overestimate the heat flux. I will the next slide. And most importantly, the neutrals might be the main heat carriers to the diverters. Now coming to why I'm saying that we have to be very careful with heat loads, because there are other effects contributing to heat loads, and one has to take these two effects of collisionality of Gs and contribution on high energy particles, electrons, which are present in the diverter plasma. These are rest of the upstream electrons which propagate in the collisionless regime, so survive collisions and come to the diverter. And these particles, this is jet-like simulation, jet-like Sol, you can see that their contribution to the local thermal velocity is very high, so you have to consider up to 20 times thermal velocity to see these particles. But unfortunately, they contribute a lot. For jet, they contribute maybe 20% or 30%, but for ITA, they can contribute together with neutrals quite a dominant part of the main heat loads. That's why we have to be careful. We have a high contribution due to higher energetic electrons and reduction of the heat loads due to collisionality of Gs. And unfortunately, there is no single, it's a case dependent. So the question is now, because we can play with simulations and make a numerical experiments, we did the following test. So we just step by step switched off different collision mechanisms. So we consider the rest of the system, so usual, so all type of collisions, Coulomb collisions, neutral ion collisions, electron ion collisions, so ionization, excitation, charge exchange, dissociation, and so we're still switched off in this area. And in the left part, so near to the Gs, we started to switch off, first of all, electron ion Coulomb collisions, and the blue one is ion-ion collisions. We have switched off, and we did not get any results. So we still, the Mach number was below 1. But when we switched on the ion-neutral charge exchange collisions, then we get back recovered, let's say, classical result. I want to say the density, there is no big difference in density or temperature between these cases, but we can see that whenever we switch all the ion and neutral collisions, mainly charge exchange collisions, we recover Mach number equal 1. So this gives us clue that there are two mechanisms responsible for this subsonic plasma flow in high density diverter plasma is Coulomb collisions, because they are responsible for building up this density and temperature, low temperatures, plus ion neutral collisions. And this will be in a much extended way presented in the oncoming EPS conference. Now, a few words about, because it's so maybe some people are interested about how bit1 code works. I have a rest of the talk devoted to the short description of bit1 code. Actually, there is a whole set of codes, so bit1, bit2, and bit3, but for this simulation, we consider just bit1. This is one-dimensional in space, three-dimensional velocity space. It's a flux tube code, so we consider one flux tube. So we have bounded by two diverters. We have plasma source inside, so mimicking cross-field transport. We have kind of synthetic diagnostics for probes and radiation. We can have a fueling, impurity seeding. So it's quite, although it's quite one, looks quite simple, but in reality quite complex code, which has a field contains electron, ion, and impurity ions, neutrals. All of them are treated full kinetic treatment of these particles. For neutrals and ions, we switch usually two-dimensional models or quasi-2D. We account for neutrals which are absorbed at the wall or across the separatrix. The same for the impurity ions. We have nonlinear particle interactions. It's a very complex model. It's an energy and momentum conserving model of M projectile and N target particles. So it has, for instance, exact model of three modular combinations of N with 3. And we have also the dissociative ionization collisions when you have N is 2 and N is 4. We have a linear model of plasma surface interaction. So altogether is about of the order of 1,000 interaction types. Numerics, it's massively parallel. We usually run on 2,000 cores, but scaling is good scaling is up to 8. I mean, 2,000 is because in queuing time is longer if you take longer, more cores. It has a unique field solvers, unique because for bit1 has a home developed solver, which has a, this very good scaling. So I don't know, we tested up to 10,000. It has a very sophisticated 2 and 3-dimensional field solvers developed for bit2 and bit3 by high-level support team. And it uses optimized memory management. And I want to concentrate on this because these two things can be achieved, or also implementation numerics interactions can be done more or less straightforward. But optimized memory management is quite unique for this code. And let me spend one slide on this. Bit1 uses natural sorting. Natural sorting means that particles carry their cell index. So it means that you have two particles which are neighboring in the memory. So particles N and N plus 1 in the cell I. They are also neighbors in the real space. What this gives? This gives a cache hit increases, because whenever we have some operation on these particles, we don't need to transfer. So in cache, you can find the same parameters, and this increase the speed up to factor of 5, typically 5. So second, parallelization is quite straightforward because you know where each particle is located. Second is very important point, which is necessary for large size finite resolution simulations, because particle trajectories are calculated with the same accuracy at each point. So if you have a, let's say, 10-meter object, and your time steps to 10 to the minus 13, so which is in for eta simulations, then the jump is so small that at the other end you cannot feel it at all. So, but in this structure, the position of particle is just its cell number. So in one-dimensional case, it's multiplied by the cell size plus position inside cell. So the only operations are made on this parameter. So position inside given cell, it can be even float because it's sufficient, and it all times smaller than the size of the cell. Otherwise, particle jumps to the next cell. The same is for three-dimensional, two-dimensional cases. And this gives possibility that at the beginning and the end of the system, the accuracy is absolutely same. If you do not do in this fine resolution, long system simulations, you get very strong numerical asymmetry in your simulations. Also, it gives very high stability in this approach. And second and third important point, that it's very simple to make collisions because you know, for instance, which particles are neighboring in the system. You don't need additional sorting, which is used in particle codes. Usually you need to make additional sorting to find which particles are to be collided. In this case, you already know all the particles which are inside this cell, and it speeds up very far simulations very significantly. Now, I come to my conclusions. So we performed quite large set of divertor plasma simulations. Altogether for SHIS was about 20 million core hours. We find out new features of the plasma SHIS, of high collisional, high density plasma SHIS. That plasma is not subsonic to the divertor. Second, the position of the SHIS edge has to be redefined, so it's not a place where Mach number equal 1, and we propose a position where last point where plasma is still magnetized. Second, the heat and to the wall and diverter plates is carried by neutrals and hot electrons and not main plasma. These effects are the consequence of common action of Coulomb and ion neutral friction, Coulomb collisions, ion neutral friction, and this will be we are working to develop corresponding analytic model and this also will be presented very soon in oncoming, as I say, PS conference. I have no time to explain. This is a very interesting effect, and we want to go further because all these cases consider demo. I mean, up to, let's say, eta relevant parameters. But if you go to demo will have one order higher density and correspondingly at least one order higher collisionality in the diverter, and one has to simply see what you'll get for the demo. So how these parameters will change for demo. For this, we need a much higher resolution, so we need 10 to 7 grid cells, which are quite challenging for one-dimensional simulation because I never did this before, and hope that the stability of code will allow to these large-scale simulations. And that's all my talk about our contribution. But as I promised at the beginning, I want to say also a few words about my experience or our experience running on simulations, other IFERC-CSC projects. So I want to say this is one of the most stable supercomputers I accessed. So during the last probably 15 years. So number of crash, so the computer, I mean, caused crashes is negligible, even zero practically. So very responsive user support service. So we don't need this very often, but whenever it happens, it's very fast. And if you ask me what I would wish, so to have as additional tools, sorry for my kind of wish, but we need some debugging tools which are simpler than TotalView. Why? Because TotalView is a professional software. It's requiring significant learning curve, and it's easy to forget. Even if you learn it, you forget it if you do not use very often, and it's our target to not use it very often, and stable codes do not require it, and at least more than 6 months we do not have, let's say, bug or new bug or some problem. So it means that you forget this TotalView, and we have to restart our knowledge about this, and also requires graphical interface. Now, if you go from the other side, what are our main problems? So I'm speaking from the particle codes mainly, so 90% and maybe even more of possible bugs, if you call them at all bugs, particle codes are related to improper memory allocation. And it's very difficult to fix. And these are not sometimes bugs, because simply if you have a Monte Carlo code, so more routines, then you have a particle are born, then you, in many cases, you cannot estimate what will be your density in advance. So you play, so you try to assume to reduce memory, because then its simulation is speeding up. On the other hand, you have to be careful, because in some cases your density can be above what you expect, and you can, or oscillations with plasma oscillations are modeled, and you can simulation can crash. So it means that sometimes it's very difficult to fix which module is causing this. And for instance, I put it for the case for bit 3, you can say about 746 routines, at least. These are just minimal accounting related to particle array reallocation. So this considers particle send and receives, inelastic collisions, volumetric particle sources. And whenever code crashes, in most cases, of course, we have some flags telling, okay, crashed here, but they didn't work in all cases. And so question will be to have very simple debugging tool, which gives you, okay, this was the memory allocation was, I think this was a small wish from our side, and thank you for your attention.
Thank you, Dr. Chakaya, for your talk and your comments to IFERC-CSC. I will ask Great Team about the another debugging tools. Okay, for a question or comment. Okay, please. Bekle-san.
Hello, David. I have a question about boundary conditions we are using. I mean, because all the people here, as I see in the talks, they are most of them not fluid. But we have these questions about sheath boundary conditions on the diverter plates, on the walls. It's one thing. And the second thing is kinetic flux limit for heat conductivity. I'm wondering if your code can help us, or you can give us some recommendations. What we are using is good or bad. And for example, for kinetic flux limit in heat conductivity, we're always using something like constants, but coming from ceiling, not from the realistic situation. Because the Spitzer heat conductivity is valid only for collisionality plasmas, and actually we're dealing with very changing collisionality, starting from pedestal going to the diverter plates. What is your feeling, and what is your advice for fluid people?
Yeah, I mean, it's very complex. I mean, question is simple, answer is very complex. If you are within the capability of available codes, so not many changes inside code is done, then usually these codes are using, as you know, the heat flux limiters. And we did this modeling for ITA, so it was kind of request from Richard to study what will be best limiting factors in a very strange way. So the alpha 0.3 is the best, gives the best approximation. I don't know why, because then I checked this for jet, then I checked for compass. Compass is smallest tokamak we simulate, it's much lower collisionality, and also there, so 0.3 is the best, let's say, zero model, so first order model to do. So the next, what we are trying to do, actually, this is number of projects we are doing and want to do this, is just to develop a corresponding local flux heat flux model to be implemented in the codes. There are some models, but they are very complex and not including, for instance, plasma impurity interaction, plasma neutral interaction. And at this moment, we are doing it, but we don't know when we finish, because it's very complex. Even comparison of 1D fluid model to 1D kinetic model, it's a really very complex task, which to our surprise takes really a lot of time. So simple answer, 0.3 is very good approximation, so you can go with this number.
Okay, thank you. We'll use it.
Okay. Any other? No? Okay, thank you, Dr. Chakaya. Yeah. So, okay, now the first half of the workshop finished. And next is virtual group photo time. Please turn on your camera for the group photo. So, と正面の画面は違うんですけど。瀬戸さんもちょっとスクリーンショット。シフトコマンド3です。OK。だいぶ取りました。Okay. Okay. Thank you for your cooperation. Now we take several photos for the workshop. That may be used for in the, some report for the IFERC project and so on. Okay, please. Thank you for your cooperation. And we take some break to 5 minutes or 10 minutes? Okay, we will take a 5 minutes break. So 5 minutes later, we will restart the workshop.
microphone issues.
So, okay, let's start the second half of the workshop. The first speaker of the second part is Dr. Yamamoto from QST. The title of talk is Study of Multiple Impurity Seeding Effect by Integrated Diverter called SONIC. So please start the Yamamoto-san.
Okay, so thank you very much for inviting me as a speaker. So I'm Shohei Yamamoto from QST Naka, and I would like to talk about the progress of our project named entitled Study of Multiple Impurity Seeding Effect by Integrated Diverter called SONIC. So first, I would like to briefly introduce about our research topic about impurity transport. As you may know, impurities play a key role for ITER and NEMO. So impurities, for example, extrinsic seeding impurities such as neon and argon, and intrinsic impurities coming from wall such as carbon and tungsten, lowers plasma temperature by radiation cooling. And this effect is useful when impurities are in diverter or solar edge regions by dissipating heat flux towards diverter plate. On the other hand, impurities in the core causes dilution and radiation cooling of core plasma, and therefore it is harmful to the core plasma performance. So in future devices, both low diverter heat load and high core plasma performance are required. So therefore it is necessary to obtain understandings of impurity transport processes, and to establish a method to control impurity transport are necessary. So in QST, we are tackling to the impurity transport problems mentioned before by means of integrated diverter called SONIC. So let me briefly introduce about SONIC code. So the SONIC consists of the fluid transport called SOLDO, and kinetic neutral transport called NU2D, and kinetic impurity transport called IMPMC. And the SONIC self-consistently computes transport processes of plasma, neutrals, and impurities. And one of the unique features of SONIC is that this computes impurity transport kinetically by IMPMC code. So in this presentation, I would like to talk about following three topics obtained by SONIC simulation. First one is the study of mixed impurity seeding of argon and neon. And second is the improved kinetic modeling of the thermal force. And last one is the benchmarking activity against SOLPS ITER. So let's move on to first topic. So I would like to talk about first topic. The single impurity seeding operation is now mainly considered in present impurity seeding strategies. So I will explain two examples for argon only and neon only. So, and radiation function as a function of electron temperature is shown in this figure, and argon is radiative in the diverter and solar and edge temperature regions. So argon can effectively contribute to the reduction of the heat flux towards diverter plates. However, as you in this figure, argon is also radiative in the core temperature regions, so it may harmful to the core performance by radiation. And on the other hand, neon is radiative in, especially in diverter region, and not so much radiative in the core region. So it is good to lower just solar diverter plasmas. But as shown in, as seen from the radiation function, it is expected to be a larger seeding rate than argon is required to obtain same amount of radiation power as argon. So dilution in the core is expected by high neon density by large seeding rates. So in order to overcome above weak points of the single noble gas seeding cases, so mixed impurity seeding of argon neon experiment is performed in JT60U, and it is reported that better core plasma performance than argon only case. So different radiation characteristics of impurity species may be possible to control impurity transport. So we have performed the argon plus neon mixed impurity seeding simulation in JT60SA. And calculation parameters are set for sonic based on typical operation parameter for JT60SA. So, and input parameters are shown here. And we have performed 2 cases of seeding impurity. So case A is argon only seeding case from the buffer port. And another case is additional injection of neon from the private port into the argon seeded case. And also intrinsic carbon impurities are considered. And here's a summary of the results. The schematic view of the argon density peaking point and direction of the net force is shown in the left figure. And 1D figure, 1D profiles of argon density and deuterium flow velocity and the net force is shown along the flux tube, 0.8 millimeter outside from separatrix is shown in right-hand side. So in argon only case, high argon density in the salt top by some thermal force can be seen. So this is the main source of argon ions into the core by diffusion in this calculation. On the other hand, in argon neon seeded case, low density in the salt top, which contributes to the low argon density in the core has been achieved. This is due to the friction force enhanced by the high D+ parallel flow towards the inner diverter region. So as shown in the middle figure, the green dotted line. So impurity, this result suggests impurity transport control in salt could be possible by mixed impurity seeding. And now we are looking into the mechanism why the D+ flow is enhanced by additional neon seeding. So left side figure shows the radiation power densities of argon and neon plotted on the same flux tube as mentioned before. So the high neon radiation power can be seen in the high field side near X point. And this and right-hand side figure shows stacked line radiation power of the neon 6+ and 7+. So this neon radiation is mainly contributed from the neon 6+ and 7+, and especially the neon radiation is mainly contributed from 7+. So we performed the additional calculation, without line radiation of neon plus, and the results shows that high D+ flow cannot be seen. So neon 7+ line radiation of the neon 7+ has a key role for lower argon density in top of soil. And this importance of neon 7+ line radiation is consistent with spectroscopic and bolometric observation in the JT60U argon and neon seeding experiment. But since sonic computes only a steady state of the plasma and impurity transport, so the present sonic cannot follow detailed mechanism of deep flow acceleration. So we recently have developed the time-dependent version of the sonic, and the detailed analysis of transient state by time dependent version of Sonic is now ongoing. So we expect good results will be coming out this year. And now let's move on to the topic 2, improved kinetic modeling of the thermal force. So the parallel impurity transport process is mainly decided by the force balance between friction and thermal forces. The friction force is proportional to the collision frequency and relative velocity between background ion and impurity. And on the other hand, the present modeling of thermal force only proportional to the temperature gradient, or I would say heat flux. So therefore, the collisionality dependence is not included in conventional thermal force modeling, which is because present thermal force model only assumes high collisional plasma. However, in demo reactor, high temperature and low density even in soil is expected, and so it may become collisionality is lower. So to improve thermal force modeling to cover lower collisional plasma condition for demo and demo soil prediction is needed. This is the motivation, and the thermal force is proportional to the heat flux. We have developed the thermal force models based on the 2 heat flux models, which is coming from a Fundamental paper. And one is a free streaming energy type model, and the second one is a generalized moment equation models. And both models include collisionality dependence as shown in this here. And a free streaming energy model includes scale length of the temperature here. And generalized moment model includes velocity scale length, so as to reduce or enhance heat conduction in low collisional plasmas. By using this heat flux, we have developed new two thermal force models. And here, this figure shows the effect of a new thermal force model compared with a conventional model with in analytic way. And as shown in this figure, new thermal force model expected to be weaker than conventional model in demo soil relevant plasma condition. So we have implemented these models into Sonic and demonstrated its effects in JA demo predictive simulation. So here's a calculation condition. CD argon is simulated in this calculation, and conventional thermal force model and the new two thermal force models are compared. And these 3 figures show the argon density for 3 cases. As seen from the figures, impurity transport simulations with new thermal force model results in lower argon density than soil upstream, as shown in these regions. And this so now I'm showing 1D argon density and net force profiles plotted along the separatics, and the lower argon density by new thermal force models can be seen especially in the high field side region. And the net force shown in the right-hand side figure show the force directing upstream in low field side is reduced. So it is expected that more argon impurities are compressed in the outer diverter region, and which is possibly explains the lower argon density in the high field side. So this result demonstrates the importance of collisionality dependence in the thermal force model in the solid plasma of demo. And last one is a benchmarking activity and SOLPS ether. However, we don't get any concrete results at present, but we have recently launched this activity, and it's ongoing under collaboration between JA, Japan, and the EU, and IO. So aim of this benchmarking is to validate and improve transport modeling of both codes. So we set 3 steps. So first step is the only reference case in JT60SA, and the step 2 is in addition to the pure plasma, the introduced curve impurities are considered in order to compare the impurity transport. And third step is extrinsic argon impurities are seeded in addition from step 2. And so far we have developed a mesh converter of a SOL-PS fluid mesh to solid mesh in order to minimize the errors coming from the difference of mesh structure as minimum as possible. And also we have installed the IMAS onto JFRS-1 for the systematic to compare the results in a more systematic way. And also in parallel, we have developed the IMAS interface for Sonic. And detailed comparison is homework for this year's project. So let me summarize my talk. First topic was the study of a mixed impurity of argon and neon seeding, and numerical simulation of Sonic shows that impurity transport control in SOL could be possible by mixed impurity seeding. So argon only seeding case, high argon density in SOL top can be seen due to the thermal force, and on the other hand, argon plus neon seeding case, the low argon density in the SOL top can be seen by enhanced friction force. So, which is enhanced by a high D plus parallel flow towards another diverter region by neon radiation. And our key is neon 7 plus line radiation in this case. And also, I should have write a future work, but we are now looking into the time transient phenomena of this effect by newly developed time-dependent version of Sonic. Second topic is the improved kinetic modeling of the thermal force, and this results demonstrate the importance of the collisionality dependence in the thermal force model in SOL plasma of demo. So 2 models of FSE and GM models of collisionality dependent thermal force have been developed. And the introduction of these forces reduced argon density in the SOL high field side upstream is reduced due to weaker thermal force effect in the low field side upstream and outer diverter region. And third topic is a benchmarking activity against SOL-PS ether. And now this is ongoing. I just studied and ongoing under collaboration between Japan, the EU, and IO. So this is end of my talk, and I'm sorry I realized that I haven't speak in English for about 1 year, so I should have make some more rehearsal. So sorry, thank you very much.
Okay, thank you, Yamamoto-san. Okay, question and comment. Dr. Chakaya, please.
Yes, Yamamoto-san, thank you very much for presentation. I don't know how long break you had, but it was very good presentation.
Thank you.
Yeah, I have a question because, you know, I think one of the presenters will speak about this today, but in European fluid community, Zhdanov closure is very popular. It's Zhdanov closure. It allows to consider collision between arbitrary ion species, and so of course includes also the thermal force. I just propose you to have a look to these works. It's called Zhdanov closure of arbitrary ion species. So it's mass, charge dependent, and quite arbitrary, complex, but still. So I propose to do this. Compare your model with Zhdanov models.
Okay, I think it's included in also SolPS as well, if I remember correctly. So maybe it's straightforward when I'm making we are include such a comparison into this benchmarking activity, I think.
Yeah, it depends which version of SOLPS you have, probably. I mean, I think it was done recently. If it's done, I'm not sure, but if it's done recently. So I think Patrick will speak about his code, and I know that it's included in his code. One of the presenters, so Patrick Tamain, will speak about his presentation today. Maybe he can clarify this, but this is quite popular. So it's just arbitrary ion-ion collision. So it's taken into account, and it's interesting to just cross-check and to score, check the speed of how it reduces the speed of the simulation and so on.
Oh, okay, I see.
Thank
okay,
you.
we will do that.
Thank you.
Thank you.
Okay. Next, Bekle-san.
Just a very quick question. Is it possible to use this code with 3D fields?
Unfortunately not, because this fluid code is only applied to 2D modeling. So if we try to do the 3D, apply to 3D field, then it will be a very massive extension is needed. So at present, it's not possible.
Okay, thank you.
So any other question or comment? Okay, no. Thank you, Yamato-san.
Thank you.
We will move on the next talk. Next speaker is Dr. Tamain from CEA. Title of the talk is Results of EBC Projects on JFRS-1. Okay, please start. It looks that Dr. Tamain is.
Yeah, Chairman, we don't see him on the participant list. So I
he cannot connect or missing the link. Okay, I will send an email to him. So, okay, I change the order of the talk. So the next speaker is Professor Imadera from Kyoto University. Imadera-san, can you give your talk?
Yeah, sure.
Oh, okay. So, next speaker is Imadera-san. Title of talk is a Global Gel Kinetic Simulation for High Beta Plasma. Okay, please start.
Okay, can you see my screen?
Yes.
Oh, okay, so let me start my presentation. I'm Kenji Imadera in Kyoto University, Japan. It's my honor to report our research at this Japan EU IFERC-CSC workshop. My presentation title is Global Gyrokinetic Simulation for High Beta Plasma, which is same as our project title. In this talk, after the brief introduction of our full F gyrokinetic code GKNet, we would like to show you two kinds of numerical results aiming at the achievement and sustainment of high beta plasma. So that the topics may be different from the other talks, but anyway, let me report our achievements. And the collaborators are Professor Ishizawa and Kishimoto. First of all, let me discuss the background of this project. The plasma beta value given by this definition is one of the important parameters for fusion plasma because it is linked to the fusion reaction rate and also related to the production of bootstrap current, which is important for steady state operations of tokamaks. To achieve and sustain high beta states, our group focuses on the following two topics. One is the study of ITB formation for the achievement of high beta plasma. Based on full F electrostatic model with hybrid electron, we have studied the spontaneous ITB formation in flux-driven ITG-TEM turbulence for the reverse magnetic shear configuration. And the other is a study of TAE-KBM interaction for the sustainment of high beta plasma. Based on delta F electromagnetic model with kinetic electron, we have studied the interaction between energy particle-driven MHD mode and drift wave turbulence. Thus, each topic has a different approach and target. Today, let me report these two kinds of results as the achievement of our project GGHB. Before moving to the numerical results, let me introduce our full F gyrokinetic code GKNet. Original GKNet is based on the full F gyrokinetic, which consists of the gyrokinetic Brasov equation for full F ion distribution function, and also the gyrokinetic quasi-neutrality condition with adiabatic electron. In full F global approach, both partable and equilibrium parts of distribution function are solved self-consistently under the power balance between external heat source and sink, which is called as flux-driven simulations, and such a typical case of flux-driven simulation will be shown in the next slide. And as a Brasov solver, we use the MOIS scheme, which was developed for fluid simulation and introduced to rectangular gyrokinetic code. We have applied it to polar coordinate with new flux conservative scheme, and this figure shows the time evolution of total energy in the case with and without new flux conservative scheme. We can see that not only exact particle conservation, but also energy conservation is much improved. In addition, the field solver is solved in real space, and full order FLR effect is taken into account by using 20-point averaging on gyro ring. And this figure shows the animation of 3D electrostatic potential and 1D ion temperature in our typical flux-driven simulation. First, mean flow is formed, and then ITG mode is driven, then saturated by zonal flow. Finally, such a quasi-steady state of turbulence, not decaying turbulence, is established by external heat source and sink. In this case, the avalanche dynamics accompanied by the turbulence becomes dominant, and the typical scale length of LT is tied to be globally constant, as is shown by such a kind of exponential function. Interestingly, such a LT does not largely change even if we increase the heat input power, showing the so-called strong profile stiffness. This is a typical tendency of our flux-driven simulation. This chart shows the recent extension of GKNet. We have extended to three different directions. One is the magnetic flux coordinate one, which enables us to treat non-circular plasma shape. Another is a global delta F electronic version with kinetic electron. On the other hand, in the electrostatic simulation with kinetic electron, so-called the omega H mode appears, which severely limits the CFL condition. To avoid this issue, we have introduced the so-called hybrid electron model. In this talk, GKNet HE is used for the internal transport barrier study, while GKNet KEM is used for the TAE-KBM interaction study. So that in this talk, we use these two kind of different versions of GKNet. And for the parallelization, high efficient 2D FFT is installed by using the 1D FFT and MPI all-to-all transport technique with the aid of communication and computation heating optimization by means of the hybrid parallelization. The following two graphs shows a strong scaling in each supercomputer, Cray XC40 in Kyoto University and Cray XT50, namely JFRS-1. In both cases, we can see the good scaling beyond the 10,000 cores. Our code consumes the most CPU time for time pushing by gyrokinetic Brasov equation and secondary collision operator because its coefficient changes in time in full F case. From such a tendency, from such a scaling, and also the fact that night running Cray XC40 is slower than JFRS-1, memory throughput in the Brasov solver seems to be the bottleneck. So now, we are improving how to improve or hide such a bottleneck now. Okay, that's all for the introduction of our full F gyrokinetic code. And then let me move to the first topics. Internal transport barrier, which acts as a shielding layer of particle and heat transport by suppressing the turbulence, has a crucial key to achieve a high-performance plasma confinement. Now, some possible trigger mechanisms for ITB formation are proposed. One is a positive feedback loop by an E cross B mean flow shown in the left flow chart. This mechanism is considered to become active once E cross B sharing rate exceeds the linear growth rates of microscale instabilities. Another is a positive feedback loop by a safety factor profile. Once turbulence is suppressed, the steepened pressure gradient drives the bootstrap current, leading to the reversal of the safety factor profile. Generally, reversed Q profile stabilizes the turbulence so that the feedback loop becomes active. The stabilization by Shafran shift is also the other candidate, especially in the high beta regime. To study such a trigger mechanism of ITB, by using our full F gyrokinetic code GKNet, which is the original version, we did the flux-driven ITG simulation. We found that the momentum injection can change mean E cross B flow through the radial force balance, which can break the burning symmetry of turbulence, leading to the ITB formation. Such a mechanism can also benefit the ITB formation around the Q minimum surface in reverse magnetic shear plasma, because This figure shows the time spatial evolution of temperature gradient in the momentum modulation test. We can see that clear ITB is formed just inside of Q minimum and then collapsed after the input is turned off. It is not shown here, but the flux gradient relationship shows the hysteresis nature, indicating the non-locality of turbulent transport and the resultant ITB formation. However, in this previous study, based on the original GKNet with adiabatic electron, enough large momentum injection is required for ITB formation in flux-driven ITG turbulence. In addition, some experiments indicate the importance of counter-intrinsic rotation, which also conflicts to our previous study. Motivated by this background, we have introduced the hybrid electron model and performed the flux-driven ITG TEM simulation for reverse magnetic shear plasma. In this study, we consider two cases. One is ITG case in which electron temperature gradient is gentle and there is no electron heat input. The other is the ITG TEM case in which electron temperature gradient is enough steep and sustained by the electron heating. Here, we introduced only heat source around the magnetic axis in both cases, which does not provide particle and momentum input to achieve spontaneous ITB formation. These three figures shows the time spatial evolutions of ER in flux-driven ITG turbulence with adiabatic electron, ITG turbulence with kinetic electron, and ITG TM turbulence with kinetic electron. From these figures, we can clearly see that stable local maximum of ER is formed near Q minimum surface only in kinetic electron case. This is because the kinetic electron dynamics can provide more unstable linear ITG instability and resultant stronger zonal flow generation. In fact, from the linear and nonlinear benchmark tests, the linear growth rate is roughly 1.7 times larger due to weak shielding effect of kinetic electron, and the established zonal flow is stronger and more corrugated. And we also found that net co-rotation is driven around Q minimum surface in kinetic electron case, as is shown in right figure. Interestingly, there exists a positive feedback mechanism between mean ER and resultant momentum diffusion because the first term and the second term has even parity across Q minimum like that, which can work to reduce the momentum diffusion like that. As a result, a peaked co-rotation profile is sustained and can keep the stable local maximum of mean ER shown in the left figure and the last page through the radial force balance, which details will be discussed later. On the other hand, in ITG-TM case, counter rotation is also observed in negative magnetic shear region, so that TEM has some role for such a counter rotation. To confirm the origin of co and counter rotation, we perform the ITG dominant and TM dominant decaying turbulence simulation in cyclone base case. These figures show the linear eigenfunction and the intrinsic rotation profile in ITG and TM cases, respectively. We can clearly see that the ITG turbulence can trigger the co-current toroidal rotation, while TM turbulence can trigger the opposite one. This originates from the fact that the finite ballooning angle of the global mode structure arising from the profile sharing effect is shown to induce a residual stress part of momentum flux. The sign of the ballooning angle between ITG and TM turbulence is opposite, so that the direction of intellectual rotation is considered to be reversed. This observation indicates that the steep electron temperature gradient is considered to selectively destabilize TM in the negative magnetic shear region, leading to opposite intrinsic rotation shown in the last page and this figure. Such a difference of intrinsic rotation is considered to provide different sustainment mechanism of ER. This figure shows the radial profile of each term in the radial force balance. In flux-driven ITG turbulence with kinetic electron, concurrent toroidal rotation can balance with ER, which here becomes strong just inside of Q minimum. On the other hand, in ITG TM turbulence case with kinetic electron, ER is reversed in the negative magnetic shear region by counter intrinsic rotation, which makes its shear stronger and pressure gradient steeper. The fact that negative ER and positive pressure gradient balance with each other indicates that the positive feedback loop by a E cross B mean flow can be active, as was discussed in the background. As a result, the ion turbulent thermal diffusivity in flux-driven ITG TM case spontaneously decreased to the neoclassical transport level from R equals 0.480 to 0.680, where ER shear becomes steep, which is a typical tendency inside the transport barrier. This result indicates that the coexistence of different modes located inside and outside can trigger the opposite direction of the intrinsic rotation. This discontinuity of intrinsic rotation can make the ER shear stronger, leading to the positive feedback by a mean E cross B flow and resultant ITP formation. This is the main result of the first topics. Then let me move to the second topics. In order to realize the high performance burning plasmas, it is necessary to reduce both energetic alpha particle transport and bulk plasma transport simultaneously. The former is mainly dominated by the macro scale MHD mode, while the latter is governed by the micro scale turbulent transport. The difficulty for such a case lies in the fact that the drift wave turbulence and the MHD modes driven by energetic particles coexist in burning plasmas. Thereby, the interaction between them is expected to take place and lead to new transport phenomena. Based on such a background, we have investigated the nonlinear interaction between the toroidal alpha eigenmode driven by energetic particles and electromagnetic drift wave turbulence by using the global delta electromagnetic version of GKNet. So upper figure shows the simulation setup. Safety factor is set to drive TAE along the half minor radius. Bulk and energetic particle pressures and its ratio is given as follows, in which both ITAE and KBM are unstable. The bottom figure shows their dispersion relation and eigenfunction. The plasma is unstable against a TAE at a low toroidal mode number n equal 2, which real frequency is located at the gap region of alpha continuum. On the other hand, kinetic ballooning mode is unstable at a high toroidal mode number from n equals 6. The corresponding eigenfunctions are found to be global for TAE and relatively local for KBM. This is a typical tendency of linear structure. On the other hand, on the nonlinear stage, we found that the interesting multi-scale interaction between such TAE and KBM. The left figure shows the spectrum of electrostatic potential in the cases with TAE plus drift wave turbulence, only KBM, and only TAE. We can see that TAE suppresses the most unstable mode like that, but enhances the smaller toroidal wave number mode, causing the inverse cascade. Due to the inverse cascaded fluctuations, the energy flux of bulk ions Qi in TAE plus drift wave turbulence case is enhanced at the middle wave number from n equals 4 to n equals 10. Such an interaction also slightly suppresses the particle flux of energetic ions, namely gamma F at n equals 1 and 2, but enhance gamma F by the inverse cascaded fluctuations. So that through the nonlinear interaction, we can see that the inverse cascade takes place, causing the energy flux of bulk ion and particle flux of energetic ions. And in addition, TAE can also change the localization of drift wave turbulence in the toroidal plane. This figure shows the toroidal distribution of the electrostatic potential amplitude for n equals 12, which corresponds to the most unstable mode of KBM. Before the growth of TAE, the drift wave turbulence is toroidally localized in the unfavorable curvature region. Then, after the development of TAE, the turbulence spreads to the favorable curvature region because of the global structure of the TAE. This spreading can suppress the most unstable drift wave mode through the geometrical damping effect. And this figure shows a diagram how the drift wave turbulence is suppressed by the TAE. The drift wave originally grows at the outside of the torus at the frame A, then becomes turbulence with the inverse cascade at the frame B. The nonlinear mode coupling of turbulence with the macro scale MHD instability transfers the energy of turbulence to the homogenized and large scale structure at the frame C. So we can conclude that TAE has two stabilization effects. One is the inverse cascade, and the other is the transfer to the such a good curvature region. Then nonlinear interaction can suppress the drift wave turbulence. Okay, so finally, let me move to the summary. First, we have performed the global electromagnetic simulation to study multi-scale nonlinear interactions between macro-scale drift wave turbulence and the toroidal alpha eigenmode, which is the macro-scale instability driven by energetic particles. As a result of the interaction, the TAE transfers the energy of turbulence from high N mode to the low N mode, causing the inverse cascade. The inverse cascade fluctuation enhances both bulk ion energy transport and fast ion particle transport. Before the growth of TAE, the drift wave turbulence is toroidally localized in the unfavorable curvature region. Then, after the development of TAE, the turbulence spread to the favorable curvature region suppressing the most unstable drift wave mode through the geometrical damping effect. And second, we have performed the flux-driven ITGTM simulation in reverse magnetic shear configuration by using the hybrid kinetic electron model. In the presence of both ion and electron heating, a counter-intrinsic rotation by TEM turbulence is driven in negative magnetic shear region, leading to stronger ER shear and resultant spontaneous larger reduction of ion turbulence thermal diffusivity. An increase of counter-intrinsic rotation is in the narrow region of the ITB located just inside of Q minimum, which is called as a notched rotation, is also observed in JT60U reverse magnetic shear discharge with balanced momentum injection. So our result implies a qualitative agreement with such an observation, and it is natural to conclude that counter-intrinsic rotation is a possible candidate to trigger the positive feedback loop via E cross B mean flow, leading to spontaneous ITB formation. And other future plans, by deflecting the bootstrap current and Shafran shift effect to the analytical magnetic equilibrium, which dispersion can treat in time, we can take them into account, and such a simulation can help us to understand the overall positive feedback loop for ITB formation. This is a summary of my talk. Thank you for your attention.
So, thank you, Imada-san. Now, question and comment time. Do you have any question or comment? So, yeah, I have a question about the ITB formation simulation. Probably in slide 12, you showed the, yes, it's okay. So you show the profile of the temperature gradient and pressure, ion pressure gradient. So in the when the kinetic electrons are included in the in your simulation, particle transport can be driven by the no adiabatic response of electrons. So how about the density profile for the ITG, kinetic ITG TEM case? So,
yeah. Okay.
So yeah,
okay.
in the figure, so you show the steep PI is created by the created. So how about the density profile?
Yeah, thank you for a very nice question. But first of all, in my case, there is no clear density ITB. And I think this is related to the simulation setup. In my case, density gradient is slightly gentle, so that the particle transport is not so strong. So that the weak density ITB is formed at the same position of temperature ITB, but such a gradient is not so large. So my expectation is if we increase the density gradient, we can see more clear particle transport dynamics and then resultant density ITB. But I have not checked yet.
Okay, thank you. So, any other question or comment? Okay, no comment, no question. Okay, thank you, Imada-san. So now Dr. Tamai is connecting to the this meeting. So so next speaker is Dr. Tamai from CEA. So The title of talk is Results of EBC Project on JFRS-1. So please start, Dr. Tamai.
Yes, hello. Sorry for my difficulties with connection before. So I try to share my screen. And move to full screen. Just let me know if you don't see or if there is any issue. Can you see the presentation now?
You can see.
Yes.
Okay, perfect. Okay, so thank you very much for inviting me to this workshop. I'm going to present today some reports of the results of a project led by Eurofusion for the development of a new European boundary plasma solver for reactor relevant conditions. And I want to stress out before starting that there has been contribution of many people to this work whose list you can find here, and I really want to acknowledge their participation there. So I start with a quick motivation. You all know that edge fluid modeling has been the key tool for analyzing exhaust issues, and in particular to design diverters and also define their operational space, in particular for ITER. This diverter that you can see here, whose size is it's a diverter. We have never built such large diverters now. And they help to analyze issues related to heat exhaust, such as heat fluxes to the targets, particle exhaust, as well as stability and performance. We don't want, for example, impurities we inject in the edge plasma to contaminate the core. So, for example, for the ITER diverter physics basis, everything was based on SolPS, two versions of SolPS actually, SolPS 4.3 and SolPS ITER, and a lot of exhaustive studies have been led with this code, leading to this kind of plot that I extracted from a paper by Richard Pitts 2 years ago, which shows the peak heat flux at the targets as a function of the divertor neutral pressure and what happens when you inject impurities. I'm not going to discuss that plot, but just to show what these codes are able to do and what they are used to for ITER. So, you heard in the title of my talk that we want to aim at building new codes for reactor relevant conditions. So why do we need a boundary code for reactors? Because there seems to be one already available for ITER. Why wouldn't it work for reactors? Well, the point is that demo will push the power exhaust challenge much further than ITER. I've extracted here a table from a talk from Ray Merdes at some IAA demo workshop. Summarizing numbers, key numbers in terms of exhaust for medium-sized tokamaks as DEX, JET, for ITER and for demo. And I think if you want to focus only on a couple of numbers, you should focus on these I have framed in red there on the bottom, where you see that the ratio of the power crossing the separatrix to the major radius, which gives you more or less the parallel flux at the target, will increase one step further by something like 10% in demo, but even worse, the ratio of this power to the toroidal field, which normally at scales like lambda q, will increase even more. So the heat exhaust challenge will be even stronger in demo, and this will put strong constraints on the operational space margin. We can't afford having numerical codes that have error bars of 50 or 60 or 100% for this kind of design study. So the reliability of predictions is critical, and they need to be really predictive. And that's where our current existing tools, and I was speaking about SolPS before, but it's not only SolPS, it's actually all the tools of this class have limits. First of all, they have missing physics. They assume transport parameters in particular, so they in fact assume decay lengths in the scrape-off layer, and they have flux limits also to account for kinetic effects, for example. And they're also, although it might seem paradoxical for people using modern HPC, very large HPC codes, but these codes are, even given their size, not enough computationally effective. So because reactor cases are extremely demanding, if you take a SolPS simulation for a medium-sized tokamak, we are talking about a few days of simulations, sometimes even a few hours. But if you move to ITER or demo cases, we are talking about months-long simulations, several months, which becomes unusable for us for exhaustive scoping studies. So the project I'm reporting today about is actually part of a larger context. It's Eurofusion that started what is called the task coordination, theory and advanced simulation coordination, with two complementary arms. The TSVV part, TSVV tasks, theory, simulation, validation, and verifications, which aim at developing state-of-the-art codes, and the advanced computing hubs that are supposed to provide support to these TSVV tasks concerning the code development. There has been a two-stage development of the strategy. There has been first pilot tasks launched in 2019 until the end of last year. And now there are 14 full-fledged tasks that have been launched in April and that will run for 5 years. If you want more details, you can go and see this link. And the project I'm going to report about today is one of these tasks, and its aim is to develop the next generation of boundary plasma fluid code for reactor-relevant applications. So the consortium of the team is represented here. It's gathering most of the European expertise in edge plasma modeling, and especially on turbulence modeling, but also on mean field modeling. You see that there are people involved in saltpeter heater. And so we hope that we have here all the expertise necessary to move forward and provide a strong contribution to the field. So what's our target? So the target is to go beyond the state of the art. And if we look at the state of the art, it's schematically composed of two legs, mean field fluid modeling codes on one side. So like SolPS, H2D, SolEdge, Sonic, which provide a very rich description of the physics in terms of plasma wall interaction, neutrals, impurity physics. And you end up with this kind of simulation. This is a West case with SolEdge, where you are able to predict, to simulate, I should say, the density equilibrium, the neutral distribution, etc., but without considering any turbulence. So the transport is fully prescribed manually. And then on the other side, you had 3D turbulence codes like Tokamak, GBS, Bal++, Grillix, Veltor. I mean, I missed many others there probably. That have developed in the last few years, but without considering any of the other boundary plasma physics issues like neutrals and impurities, and even describing a realistic shape for the plasma. But these codes are have now made huge progress, and they are now mature enough to integrate progressively the physics that is in 2D mean field codes into them. So if we look at the limits of each of these class of codes, what are they? So for mean field codes, the main one is, as I said, there is no turbulence physics. So perpendicular transport is a free parameter. We are prescribing the lambda Q, and so it's as reliable in terms of predictivity as scaling laws, in fact. And as I said, they are even too slow for large scope interest studies. Now, if you look at 3D turbulence codes, as I said, they miss most of the physics around plasma turbulence. So they miss the neutral description, recycling, they miss multi-species capabilities. And for the moment, they are not usable for large-scale devices because of memory or CPU time limits. And then there are also some limits that are common to both types of codes, which are the fact that fluid models are not adapted to the range of reactor-relevant conditions. You start varying between extremely small and extremely large values. There is a question about the validity of bomb boundary conditions, and I'm sure that David Sakaya spoke to you about this before. And there are questions also about the geometrical capabilities of these codes, because most of these codes at the moment are not able to model the wall geometry in its full reality. So all these points are addressed in the project, but I'm going to focus today on only 5 of them. So the turbulence physics aspects, the fluid models, the geometry, the neutrals, and also the optimization of the code. So we have worked in the last year and a half on developing full F gyrofluid models. What's the reason for that? Is that gyrofluid models are the current workhorse in edge plasma modeling. They are used in mean fields and in turbulence codes. And they are based on a collisional Bragg-Skurs-Danov closure. And this collisional aspect will be problematic when you move to demo cases. If you take a demo equilibrium there and you look at the plasma conditions at these red, blue, and green positions there, so top of pedestal, upstream scraper flare, and target plates, you see that you vary up to 6 orders of magnitude in terms of electron collision time. And close to the target space, you're extremely collisional, maybe even too much for bomb boundary conditions. And in the pedestal, you're very little collisional, which is a problem for fluid closures. So we need to work on something better than drift fluid models. And the long-term target of the project is full F gyrofluid models. Why? Because they are able to capture key kinetic effects even at low nu star, plus they have natural diametric cancellation. Second, there is also an advantage there is that their equation structure is extremely similar to drift fluid models. So any numerical method we're developing at the moment in existing codes will be applicable to gyrofluid models. And the only drawback, which is a big one, and that's what we're working on now, is the fact that these codes come for the moment are incomplete. They miss closures and they miss proper boundary conditions to be developed and tested and implemented in code. So we've worked on that. So in a team, part of our team has worked on developing an n moments gyrofluid model. So this consists in taking a projection of the gyrokinetic equation and projecting it on an arbitrary number of fluid moments using Hermite-Lager polynomials. And we have even expanded the full nonlinear gyrokinetic Coulomb collision operator. So this was published in a paper by Jorge et al. In 2019. And now we are at the phase of testing this numerically. So first numerical implementation of this model has been performed with a linearized version of the model. And this allowed us already to test the ITG turbulence or instability behavior as a function of the collisionarity. And you see here an example where you have the growth rate plotted as a function of the collisionarity. And the various curves here represent the number of moments that have been retained in the model. So this model can stop the fluid hierarchy, the gyrofluid hierarchy at 2, 3, 4, 5, 6, whatever number of moments. And what you see there is that the dashed lines show the fluid limit, which fails at capturing the kinetic limit at low collisionarity, which is a black dashed line. While if you add moments in this kind of gyrofluid model, very quickly, even already at 4 moments, you already manage to capture quite well the kinetic limit. So this is very promising because this shows that these models have the capability to capture even fully kinetic effects at very low collisionarities and could be applicable then up to the pedestal top in them. Okay, another progress on the modeling side, but this time looking a bit lower on the hierarchy of models, we can also consider trying to improve mean field codes, not only by adding turbulence directly in them, but by modeling turbulence with some kind of reduced model. And we have spent some time in the project doing this. We have for this developed a heuristic, what we call K epsilon model, which is inspired from Reynolds average and Navier-Stokes models in computational fluid dynamics. So what are these models? These models, in fact, consist in adding equations in the mean field fluid equations used in codes like SOLPS or SOLAGE 2D. 2 equations to describe the dynamics of the turbulence energy kappa here and the dissipation rate of this turbulence energy epsilon. So these are transport equations, very simple, including some growth rates that are then closed based on turbulence physics. And the diffusion coefficient is not anymore a prescribed parameter in this case of model. It's the result of it's self-consistently calculated based on the amplitude of turbulence and of its damping rate. And so if you put the right ingredients in the growth rates here of kappa and of epsilon, you can have the hope to capture much better the physics of turbulence than with very simple diffusion coefficients that are prescribed by hand. And so these models need to be closed, obviously, to these coefficients gamma, kappa, gamma, epsilon, and C nu must be defined. And the closure relies on theoretical considerations on leading instabilities, as I said. So in the examples I'm going to show now, we are based on the interchange instability and also assumptions on the dissipation rate of turbulence, which is here tuned in order to get a Kolmogorov-like cascade towards a small scale. And then finally, we also tune the closure to match the experimental scaling law for lambda Q. So overall, if you apply all these closures, you end up with a model that has a single free parameter, which is the CV parameter, which gives you the proportionality rate between the diffusion coefficient for particle transport and the intensity of turbulence. And with this single free parameter, you're able to fully consistently determine transport at every point in space and at almost negligible extra computing cost compared to codes like SOLPS. So some results. We have applied this type model to experiments, actually to experiments on two machines, TCV and West. We have tuned this CV parameter that I was speaking about before in order to match the 1 pulse on TCV. And then we tried, without changing this parameter anymore, to match pulses on TCV and on West. And what we found is showed here in 2 view graphs is that globally we have a remarkable agreement in both machines with several plasma configurations, several plasma shapes, once we had tuned CVs. And this was done, as I said, once and for all. And this is an example in the West where you see at the target plate, as a function of the coordinate along the target plate, the parallel heat flux profile arriving at the target measured by Langmuir probes. This is the dot points. And the fit that can be applied to it based on the IFERC is the blue dashed line. And what was found by Solis to decode using this Cape Silent model without any tuning of any free parameter is this black line. So an excellent match, and in particular the width of the square portfolio is matched within 20%, in fact, without any tuning. On top of that, what you get on top for free with this kind of model is that you get the spatial distribution of turbulence transport naturally because of this growth rate that is present here in the equation for K, which depend on the interchange stability. The amplitude of turbulence and the amplitude of the coefficient, transport coefficient, will be naturally ballooned. And this is what you observe here in this plot of TCV case, where we have plotted the diffusion coefficient found in this model in the TCV case. So I'm moving now to what is the main missing point now in edge turbulence code, which is neutrals. So as I said, until now, neutrals have essentially been ignored in turbulence codes due to the difficulty already to model turbulence in 3D in the edge plasma. But we know that neutrals are mandatory for reactor relevant studies. In large devices, the recycling source is up to 100 times larger, even more than the fueling source. Just to convince yourself, this is an example of the ionization of particles, the ionization of particles in an ITER case provided with Solis 2D. And in fact, this simulation is driven by a gas puff here at the top of the machine. If you have good eyes, you might see that there is small red spot here. So this is the fueling, and this is recycling. And if you integrate the sources, you find that the recycling is more than 100 times larger than fueling. So it's kind of difficult to ignore that. And second, numerous experiments indicate that there's an impact of recycling regimes on turbulence with the well-known density shoulder. I give here references. And also some papers have mentioned that turbulence on the opposite has an impact on atomic and nuclear physics. So we really need to take both these aspects of physics together. Until now, only proof of principle coupling between turbulence code and neutrals have already been performed in ideal, and they were done only in idealistic conditions. So either very reduced geometries, attached conditions, or with incomplete neutral terms in the plasma model. So we've been working on that in the frame of the project. I will show a few slides on this. So first, we worked on this based on relatively simple 2D turbulence models, but in which we tested relatively advanced free neutral models in order to kind of capture partly the kinetic aspects of the neutrals physics. Separate isothermal neutral species are considered with characteristic temperatures corresponding to the neutral origin. So instead of having a single neutral species for deuterium, for example, we take 3 of them, one corresponding to recycling neutrals that are very cold, one corresponding to Frank-Cadden neutrals, which are hotter and correspond to a specific temperature, and another one corresponding to charge exchange neutrals at the same temperature as the ions of the plasma. And the results of this are showed here with an extract of this paper, is that, first of all, taking into account the neutrals physics has a strong impact on the filamentary dynamics. So if you seed filaments and you let them evolve in these simulations, this is what you get without neutrals above, with these well-known mushroom-shaped structures. And with neutrals, you see that the filament actually will not go as fast, will tend to even go backward at the end of its trajectory. And so the neutrals actually change a lot the dynamics there. Second, these studies also show that it's very important to take self-consistently into account the neutral terms in the vorticity equation, so the perpendicular momentum balance equations, which has not been done very properly until now in turbulence codes that have attempted to include neutral. So this is a lesson to learn for the future. Another thing that has been done in the project, we move, of course, towards more complex geometries, even realistic 3D geometries within the Grillix and Soleil-3X codes, still with free neutrals. You have here examples of Soleil-3X simulations performed for a TCV case with the particle, a snapshot of the electron density, neutral density here, and the radiation pattern that would be observed if a fast camera was pointed towards this plasma. And the same kind of radiation pattern obtained with a Grillix simulation in an SDX case. And what is found in these two codes is that adding neutrals in turbulence codes allows a much better match of the simulations with respect to experiments, in particular on density profiles and temperature profiles. So that's the good news. The bad news is that neutrals recycling strongly increases the simulation equilibration time. So instead of running a simulation for a few tens of milliseconds to get a good equilibrium, steady state equilibrium with turbulence, you have to wait now much longer. Typically the ratio is 1/1 minus the effective recycling coefficient, and this one in metallic machine is very, very close to 1. So you have to multiply the duration of your simulations by typically 10 to 100 times. So this is extremely costly, and this is something that we'll need to deal with in the future. So this was with free neutrals. Now moving to kinetic neutrals, which we know are necessary for when we move to high recycling regimes. So there are two actions that have been started. I'm not going to detail results here because they are just at the beginning. But we have, on one hand, coupled the Irene Monte Carlo kinetic neutrals codes to Soleil-3X turbulence code. For the moment, it's only exploited in 2D midfield simulations. This is an extract of an ITER simulation without turbulence with this code Soleil-3X, which is capable of turbulence, but here is used without turbulence. And moving to turbulence simulations will raise additional open questions that will be addressed by the project in the next few years, in particular concerning the time discretization of this coupling. How do we couple to Irene or turbulence code in the presence of fluctuations, and how can we increase the time order of the coupling, because the time order is extremely important for turbulence discretization. A second path that we are trying to follow is the development of a fundamentally different method for treating neutral, which is the method of characteristics. It's a method based on line path integrals, which has the advantage of having no Monte Carlo noise compared with Irene, and can be generalized even to treat ionized species such as D2+ molecules. It's being tested now in GBS, so I'm not going to see much of it, but there are preliminary results as exhibited by this graph, which shows the neutral density distribution in a limited case in GBS. But there are still open questions also that the project will address. So I'm moving now to a big chunk of the project, which is the self-consistent integration of Hall and magnetic geometries, realistic Hall and magnetic geometry. So what's the issue there? The issue is illustrated with this very simple figure here, is the fact that the Hall geometry in the machine is rarely conformal with the magnetic geometry. So here it's a limited case, but it remains the same even in diverted cases. And so if you try to mesh these plasmas, and in general the meshes are aligned with flux surfaces, although it's not always the case, what you find is that the Hall is actually going through the mesh in diagonal of mesh cells, as is shown as this zoom there, which is extremely difficult then to treat the boundary conditions. And that's a limit even for 2D min-free codes now. And we know it's mandatory to treat the Hall properly for PWI issues. So we need to move forward on this. 3 parallel options have been explored. I'm going to detail only one today. So one is the use of penalization techniques, immersed boundary conditions. The second one is to develop a specific discretization scheme at the boundary, which is also going to be explored by some people in the group. And the last one I'm going to discuss now is the use of finite element discretization based on HDG method, hybrid discontinuous Galerkin method. So in the frame of the project, we developed a hybrid discontinuous Galerkin boundary plasma solver because it appeared that finite elements methods offer the flexibility to treat magnetic and Hall geometry self-consistently already with methods that are readily usable off the shelf, contrary to the other methods that require development. Our choice have been made on the hybrid discontinuous Galerkin approach. The reason for that is that it's a highly parallelizable finite element method. It has easy adaptivity, both for resolution, age, and also for order of polynomials descriptions. And it's known to be very robust. And we have also, it has already been tested for reduced plasma models in these papers. The negative aspects are the fact that it's much more complex to implement than standard finite differences or finite volume approaches. And there's also little experience for H plasma modeling, especially with turbulence. So we are kind of pioneering here and facing the first problems with this kind of method. So the project here aimed at developing a new HP adaptative European HDG solver, the so-called EPC, hence the title, the preliminary title of this presentation. And we have started the development of this EBC, but it's a large code, it's complex, as I said, and in the time frame of the project, we were not yet able to get to productive production state. But in parallel, we have used existing HDG solver, the solid HDG solver, to test model implementation in support, and I'm going to discuss this now. And I'm going to illustrate actually how powerful this HDG method can be with two examples. The first one is the demonstration that this approach can be used to analyze equilibrium independent simulations. So we have implemented in an HDG solver a 2D mean field model with free neutrals. And in fact, if you look at the mesh that is showed here, which is a finite elements mesh, you see that this mesh is not at all dependent on the plasma equilibrium, which is overlaid in red there. And so we can evolve this equilibrium on top of the mesh without changing the mesh, which is a huge advantage compared to standard approaches that are used in most mean field codes currently. And so thanks to that, you can actually simulate a whole pulse from breakdown to termination based on a single mesh. And this is what we did on the West case. And so it's a video, so I hope it's going to go through on Zoom. But so this is the start of the plasma on West, touching both the outer and the inner wall. And you have four panels here: electron density, electron temperature, parallel Mach number, so parallel velocity, and neutral density. And you see that, you will see if I click there, and hopefully you will see the video, that we are able to simulate the whole discharge, the formation of the X point here at the bottom of the machine, then the move of the X point away from the target plates. And you see that all this is treated dynamically with the neutral pressure building up progressively and so on. So so we have a plasma solver now, which, okay, has only 3 neutrals yet for the moment, but demonstrates a huge, very strong capability at treating realistic geometries. You see that there's a very complex shape here, and without regrading. And so then this can be applied to comparing to experiments, which has been done. And the circles here are what was obtained in the previous set for a few coincidences that we need to still analyze but missing. And another type of study that can be done that is also extremely promising is that then we can use this kind of simulation to analyze tungsten erosion based on the ERO2 code. And you can analyze this tungsten erosion dynamically from the start of the discharge, and you end up with this kind of simulation showing the tungsten being scraped off the wall in the limited phase at the beginning of the discharge, contaminating the core of the plasma. And then when the X point is finally formed, this tungsten that was put in the discharge initially stays there. And this is actually the bulk, the main part of the tungsten contamination of the plasma in this discharge according to the simulation. If you take a simulation, if I pause the simulation, I go to the steady state part here. If you take a simulation in steady state directly and ignore the initial part of the discharge, you get 3 times low and blobs simulate established turbulence. Now, I'm going to finish on something very numerical, but this is quite important to the project. I said that one of the problems of turbulence codes at the moment is that they are too slow for large-scale devices, and the main bottleneck of all fluid codes at the moment for turbulence is an elliptic solver, which is essential to compute electromagnetic potentials, in particular the electrostatic potential. And in some of the codes involved in the project, it represents more than 90% of the computing time. You end up with a huge matrix to invert, looking typically like this. This is a very small example, but matrix that is typically millions by millions of sides, and it changes at each time step, which is extremely time consuming. So we have started an activity which has yielded first results, but these are really preliminary results for the moment, with a performance analysis of these available linear solvers for this type of matrix with our EPFL colleagues. And it was found that the use of algebraic multigrid solver, in particular the Hyper library, with as a preconditioner with a JFRS method, was very promising and allowed us to get a factor of 20 improvement of the parallel efficiency compared with a direct solver like MERMS on 64 core. And now the project in the next few years, well, months and year, will focus on trying to move to GPU for this bottleneck. So I have two last slides to finish to discuss, because you might be wondering where is JFRS-1 here in this presentation. In fact, we have used JFRS time in 2020 for actually a very minor part of the project. It was used by our GBS code colleagues to run 3D turbulence simulations and analyze the dependency of the scraper fluids with collision rating and heating power in full-scale TCV simulations. It allowed them to derive some theory-based scaling law for the near and far Soul decay lengths. And you can see here an extract of this paper that has been submitted to Nuclear Fusion that shows the near scraper layer decay lengths for the pressure and the far scraper layer decay length for the pressure, and compared the points, the values found by GBS and the values predicted by the scaling law. And the points are the simulations, all the simulations that were performed by GBS, by the GBS team on the JFRS-1 computer. So each simulation there is several 100,000 hours of CPU time. So it's quite a significant amount of CPU time. And this allowed them to build this database and extract these scaling laws for the scraper fluid decay length. It has also to be understood that this is important for the project as a whole, because the TCV case is seen as a first step for a step ladder towards ITER simulations. TCV is a medium, small size tokamaks. We will move then to larger size like ASDEX or even JET, and then we can move to ITER. And so the demonstration that we can do full-scale TCV simulations now with 3D turbulence codes is already quite an achievement. Just a quick feedback. I didn't get that, so I don't have much details to give here. This is the answer I got from the GBS team when I asked them what were their feedback on the usage of the JFRS-1 supercomputer. And their answer was that it was a very positive experience overall with the machine, and particularly with the support team. They had initial difficulties with the installation and the execution of the code, especially with very poor performances of GBS. But thanks to a close interaction with the help desk, they managed to solve the issue. And now they are running with performances that are significantly better than on Marconi. So that's very good. Yeah. So in conclusion, I've presented you the key results of the first year of a European effort, joint effort towards the development of a next generation boundary plasma fluid code for reactor relevant applications. The approach of the project is two-stage, with first, and that's what I reported now, a multifrontal approach of upstream issues. So identify problems that are blocking points towards demo simulations, develop and test solutions in existing codes, capitalizing on their specificities. Some codes that we have now are very good in order to look at neutrals issues, for example. Some others are better to look at geometrical aspects. And then make an assessment of the situation in 2 to 3 years and converge the effort towards a reduced set of tools by integrating the best approaches that will have been identified. So in this pilot phase, I presented today 3 main points, but we have made progress along 3 lines essentially. So the development of hierarchy of models from full F gyrofluid models, I said a word on this, and also reduced turbulence models that could be used as an intermediate modeling point between mean field simulations like SOLPS or SONIC now and fully 3D turbulence code. And we have also showed that we could obtain successful initial implementation of mutual and multi-species physics in 3D turbulence codes. And progress is also ongoing on the numerical treatments, both on the geometrical aspects. The HDG solver, for example, is part of this effort, but also on numerical methods. And this is what I showed concerning the linear solver aspect of it. So thank you for your attention. If you have any question, I'm happy to answer.
Thank you, Dr. Tamain. And Dr. Chagan, please.
Yeah, thank you. I mean, thank you for a very impressive presentation, Patrick. Really very nice results. May I ask a question about your simulations of when you show these movies? What do you do? How do you do the? First of all, do you include really the core plasma? Is it just part of simulation or not? And second, what do you do with transport coefficients? Because it changes this time. Plasma parameters are these transport coefficients of diffusion, anomalous diffusion, and heat conductivity. Are they fixed or they change?
Yes. So that's thank you for the question. I actually forgot to mention it because that's actually a positive point also of this finite element approach, like HGG, is the fact that the mesh can extend up to the core. Unfortunately, the picture I put in the previous slide there, the mesh did not extend up to the core, but in this simulation, the mesh extends up to the core. So the simulation is up to the core with volumetric heat sources to drive the plasma. There is no issue with metric or that you can have with when you have structured meshes, for example. For the second question, the model that is in there for the moment is relatively simple. So we have not tried yet to implement anything like the Cape Silo model or anything like this. So the diffusion coefficients were held constant everywhere, constant in time and in space. But there is nothing a priori blocking. Obviously, I should not be too confident. There are always issues that we don't expect, but there is nothing a priori blocking with putting some transport models in there now. So either Cape Silent model or some models from the core plasma community for the closed field lines, for example, in order to get a more self-consistent description of the transport.
Thank you very much.
Okay, any other question or comment? No? Okay. Yeah. Thank you, Dr. Tamain.
Thank you very much.
Okay. So now in the workshop, all talks from the simulation projects completed. So now this workshop reached the last item, conclusion by the Professor Nakajima. Nakajima-san is chair of Joint Allocation Committee and deputy IFERC project leader from NIFS. Nakajima-san is now connected. Okay. Okay, please start.
Okay. So we are behind the schedule. So then first of all, thank you very much for attending this the IFERC-CSC workshop, and also for presenting some interesting and also the valuable presentations and talks. I think indeed this type of meeting or workshop is very meaningful, partially because we can recognize the progress of each project, and also I think the mutual interaction among users will be accelerated later. Okay. Then I'd like to mention one thing. Okay, and as you see, our project is strongly encourage the BS simulation project by using a JFRS-1 provided by QST. And in order to strengthen this encouragement, now we are revising or reconstruct the IFERC website. And where you can see, we can show of our activities in the BFA2. Okay. And in the case of IFERC-CSC activity, we will present an item named user information, okay, where you can see the information on ongoing and past BA simulation projects, okay, and although some useful information. This website will be opened soon, so then please visit it and give us your feedback when you can see the newly developed IFERC website. Again, thank you very much for attending the meeting and presenting some very nice talks. Thank you.
Okay, thank you, Nakajima-san. We had some problems in the connection, but the workshop was successfully completed by your cooperation. Yeah, thank you all for participation to the workshop. We close the meeting. Okay, so goodbye.
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 Bye. Thank you very much.
Bye.
Bye.
Thank you.
Bye bye.
Bye.
Bye.